Hi there. Today I'm going to be answering this question: which corrosion protection technique would be best for aluminum, steel, and tin? And in the process, we want to minimize cost and we want to minimize environmental impact. So this entire question can be answered with this table, which is called a standard reduction potential table. It can be found in any Gen Chem textbook. Whether you're in high school or college, this will be in there. Okay, so let's talk about why it's called a standard reduction potential table. Well, it's called a reduction potential table because everything on this table is put in the form of a reduction reaction. Lithium plus an electron goes to lithium solid. Lithium is gaining an electron is reduction. The reason it's called a standard reduction potential table is because every one of these values is just measured against a standard. That standard is 2H2 plus 2 electrons goes to H2. That is defined as 0, and then everything else is just measured against that. Okay, so if we look at this example of lithium again, lithium plus an electron goes to lithium solid. The half cell potential for that reduction is minus 3.05 volts. That is a very large negative number. Okay, so what that tells us is lithium really doesn't want to be reduced. That makes sense, right? Because when you take a piece of lithium metal and you throw it into water, it starts burning and exploding and doing all that stuff because it just wants to be lithium plus. So something doesn't want to be reduced can be conversely viewed as something wants to be oxidized. So if something doesn't want to be reduced, it wants to be oxidized. Anything with a more negative number is more easily oxidized. Okay, so that brings us around to the question. The question is, what corrosion protection technique is best? So when you're looking for protection from corrosion, what you're looking for is really protection from oxidation. You don't want your iron or steel bridge turning into a rust bridge by oxidizing the iron to iron 2 or iron 3, which is the form iron is in rust. So we just need to find something to protect iron from getting oxidized. Now, the way you do that is you just find something that's more easily oxidized than iron and put it on the iron. So we have iron down here. Iron 2 plus 2 electrons goes to iron solid. So anything higher up on the table could be used. We could use chromium, we could use zinc, we could use manganese, any of those. Now what's most commonly used is zinc. If we look at anodized nails or sacrificial anodes on bridges and dams, they're generally zinc. And the reason for that is, 1, it's more easily oxidized than iron, 2, it's dirt cheap, and 3, the environmental impact isn't too bad. So the way you can figure those out in terms of cost, you can just look that up. But in terms of something's environmental impact, probably the best way is to go to EPA's website and look up the MCL, or maximum concentration limit, for each metal. So the lower that level is, the lower the maximum concentration limit is, the more hazardous it is. So the less you want to release it into the environment. Okay, so steel is basically just iron with a little bit of carbon mixed in. So what I discussed with iron would all make sense. Now, for iron, zinc is usually used. Chromium has a very low MCL and is quite toxic, so we wouldn't want to use that. So zinc is really commonly used. Aluminum, so aluminum's up here. We just need to find something with a more negative half cell potential for reduction. So if you look here, there's beryllium. Beryllium's toxic. We don't want to use that. Magnesium, that would be a good choice. Magnesium would certainly be a good option here. And then tin, well, tin's way down here, so we could pick anything higher up. Nickel, cobalt, cadmium, chromium, iron, all of these would work. What I'd say is use iron, because iron is cheap, it is not particularly toxic, and things like cadmium, chromium, nickel, cobalt are both way more expensive and way more environmentally hazardous. So that's your answer.